This meeting is being recorded.
In the last section that we will review of Chapter 17, 17.8 discusses spectroscopy of aromatic compounds. So we'll take a look at here the IR spectra, the certain bands of absorption that we should note. So first here we have between 3,000 and 3,100 reciprocal centimeters, we see a sp2 hybridized carbon CH stretch. We'll note this on the spectrum shown on the next slide. This is generally weak or medium intensity. So we'll see one or more signals above 3,000 in this range here. And our second range that we should pay attention to is somewhere between 1,700 and 2,000. We'll look at what these look like, but they're referred to as combination bands and overtones. And again, these are usually very weak signals in this region, but they're generally present. Then we have between this band here, 1450 to 1650, we have the carbon-carbon bonds as well as ring vibrations. So we have stretching and vibrating. These three signals are generally there of medium intensity. So we have one around 1450, 1500, and then 1600. Then we have some bending in plane around 1000 to 1275. We can see several signals of strong intensity here. And then between 690 and 900, we can have out of plane CH bending. And there's usually one or two strong signals present here. So let's take a look at a representative spectrum for ethyl benzene here. And we can see that sp2 CH stretch over here above 3,000. Actually, we see two signals here. These combination band overtones, again, in this range here, right, between here and here. Then we have these stretching and ring vibrations in this region here. Then we have our CH bends, anywhere between 690 up to 900 or so. We have that bending in plane or out of plane. So these are the distinct patterns that you should see for IR spectra. We can also generalize some patterns with proton NMR, and aromatic protons generally will appear between 6.5 and 8 parts per million for their chemical shift. So that's what's shown down here. We have our aromatic protons above 7 here, and we can see the integration of these signals here. So this represents these three protons in the ethyl substituent. This signal here of this quartet would represent these two protons in the ethyl substituent. And that's how we know this integration of 5 here would represent these 5 protons in our aromatic ring. This next slide discusses the integration and splitting. So as I noted before, this signal integration would show you that there's 4 hydrogen atoms. We would have one signal here, one singlet, that's representative of these 4 hydrogens. We have this di-substituted benzene ring, or a ring with multiple substituents, but they are the same. So we produce one signal that would integrate to show all 4 protons. And again, this is in that 7 or so part per million shift range. Then we see 2 doublets somewhere between 6.5 and 8 when we have, again, a di-substituted benzene ring, but we would have 2 different types of protons that appear in our signal. So we would have our red protons show up as one signal and our blue as another. And that would produce 2 doublets. And this last line here shows us the carbon-13 NMR expected signals. So if we have a benzene ring, those carbons typically appear between 100 to 150 part per million shift. If we have a di-substituted benzene ring, we would see 2 different carbon NMR signals. If we have, so this is in a para type of orientation, then we have this ortho orientation here. we would see 3 distinct signals here. And then we have these other variations of a di-substituted benzene ring with 2 different substituents. We would produce 6 signals in either of these variations here. And here we have a monosubstituted, which would produce 4 distinct signals, a di-substituted with 4 distinct signals, and this other variation, we have a para orientation of 2 different substituents, and that would produce 4 distinct signals. So the number of signals, if you know that ahead of time, this can be helpful to, or I'm sorry, if you know the substitution pattern ahead of time, you can predict signals, or if you don't know the substitution pattern, the number of signals can help you figure out the substitution pattern of your benzene ring.